Hi friends, this is pH 4501, specific heat or the thermal property of a solid material. In the thermal property, we will be underlining the property like a specific heat, thermal expansion, and therefore let's begin with the specific heat. In this case, we have observed that there are in the beginning era of the scientific society, there was no model, not a single model rather, to have the concept and the theory for speculating the experimental evidence. Whatever the energy variations scientists have observed during the experiment with a different material, but they don't have any theoretical model for this. So in the beginning of the 19th or rather 1890, Dulong and Petit, two scientists, has given the very first proposed model for the specific heat. As it was the very first model for speculating the specific heat on the basis of theory, it was widely used in those days, but later on it is realized that it is not a universally true, especially for the lighter elements, which is the beginning, the atomic beginning phase of the atomic periodic table, like a boron, heliums. So such cases where this Dulong-Petit law is going to be fails. For heavier metal, yes, it is quite true. The second limitations of this law was just very much true in the case of approaching to their melting point and so on. So in the mid zone of the temperature, right from the 0 to approaching to the melting point, there was a variations of the specific heat which was not followed by this theory or the Dulong-Petit law. So anyway, we will see what exactly happening. So specific heat we had already learned in 9th grade, 10th grade or maybe 11th grade, that it is the desired or the required heat to raise the temperature of a 1 kg material by a 1 centigrade. Some books are also referring that 1 kg material by 1 Kelvin. So temperature could be recorded either Kelvin or the centigrade, it's not an issue. So specific heat is that, but more widely well known specific heat is used by the physicist or the chemist in the scientific society is the molecular specific heat. That means they referred about the 1 kilomole, 1 mole material and the required heat to raise the temperature by 1 degree centigrade or the 1 Kelvin is called the molecular specific heat. The importance of a molecular specific heat is once you know this their gram weight in terms of mole, then you can speculate about the number of molecules or the atom within the system, and which will be much easier to judge for the trend of the mathematical model which is proposed by the Dulong and Petit. So let us have a look what exactly the specific heat it is and how it can be measured for the any particular material. So according to the thermodynamics first law, we have seen that it is represented by dq, the first law of thermodynamics. It is represented by dq is equal to du minus d omega. So the change of the total energy minus work done. So that is a change in the heat. So du, that is a change in the total energy, minus dw can be written as a pdv, where dv is a change in the volume. So if I will restrict my specific heat at the constant volume, that means material doesn't change its volume, that means dv will be 0. So last term will be vanish off, and my equation become du is equal to dq. The thermodynamics law will permit to write it out, du is equal to dq. Now when the temperature will change, naturally heat will be changed, so I can write it out the change in as we had carried out the definition for specific heat, the title, that is a change in the temperature by raising a 1 degree, or required the amount of heat to given a material by raising a 1 temperature, 1 degree centigrade or 1 degree Kelvin. So that is a change in the heat will be occurred. So rate of change of Q with respect to rate of change of temperature, and therefore on RHS I can write it out du by dt. So that is nothing but, as it is dV is equal to constant, so I can say Cv. C is the specific heat, suffix V give me the permission to write it out constant at volume. So Cv is equal to dq by dt, which is nothing but a rate of change of total energy associated to system with respect to rate of change. माने यहाँ पे एक एग्जांपल दिया गया है कि 1 किलो वाटर है मेरे पास, तो अगर उसका 1 केल्विन सेंटीग्रेड मुझे 1 केल्विन टेम्परेचर बढ़ाना है, देन आई नीड टू सप्लाई अ heat is about 4184 joule, and the specific heat must be different for each and every different material, because there is a crystalline structure, or their structures are different, and as their molecule setup or the structures are different, so the rate of absorption of a heat and releasing of the heat is also different. And the very empirical truth they do have, that is a 1 kg copper लिया और उसमें उतनी ही heat डाली, then the raise of temperature is about 11 Kelvin, which is a 11 time high. That means rate of absorption of a heat by copper is much higher than the rate of absorption of a heat in a water. So ऐसा तो पता चलता था कि temperature the specific heat is different for a different material, right? And now how to put it on the piece of paper as a model. So Dulong and Petit have given some speculations about their models, and then they carried out the entire one. So as I told you in beginning, the heat capacity per kilomole of a substance is called a molar specific heat, and it is always advisable to underline the molecular specific heat, because you having a very specific number of molecules you can underline. Okay, so that is whole the idea. They have said that in the Dulong-Petit law, they have said that the temperature is almost, or the elevated temperature Cv is very much flat, and that is remain almost constant, that is a 3 Ru, or the Rydberg constant, 3 times of Rydberg constants per kilomole for all solids, right? So this is something the outcome is very much different they have observed. In a way it is true, and only true in the case of approaching to the their melting point. So Dulong and Petit law, it holds very good just below the melting temperature. Then this is 100% true that their specific heat is equivalence of the 3R. But in between approaching to the melting temperature to the 0 Kelvin, this is not true. In between this zone, it is following the T-cube behavior. So we will discuss later part at what exactly it means. We shall consider the crystal composed of the n number of the atoms together in the periodicity. So right now when we are speculating any model, so it's always easy and approachable if we are taking the crystalline material, because in amorphous the materials are randomized, so we don't know how to speculate and how to model or how to channelize their internal reactions and internal vibrations with them. So it's always advisable or rather in our syllabus it is model is based on the solid material. So we will list focus on the liquid as well as the gaseous molecule. Okay, and they are also putting that the approximation is obeys the Hooke's law. So the vibrations of the atoms because of the heat is pertaining about their equilibrium position, but they follows the Hooke's law. So here there are some table is given for the specific heat: copper, aluminum, iron, nickel, lead and the silver. All the metals are given over here, and it's always running in between the 0.3 to 0.2 in between. But let us say graphite having extraordinary heat absorption criteria. Water is also having a tremendous high heat absorption or the specific heat property. And many if you look at the molecular weight for each and every elements, then there is no correlation you can directly speculate about it. So it is like that. So what exactly the scenario for this one, we will check it up shortly. CV versus temperature. So the basic trend of the specific heat for almost all material is like this. At a melting point, the molecules get scattered. That means it changes their phases from solid to the liquid, and when they will move to the liquid, the rotational orientation is also incorporated. So rather than the 3 degree of freedom once it's in a solid, but when you entered into the liquid, you may have a 5 degree of freedom, and therefore the specific heat will shoot up. But well, it is not our part of syllabus, so we will not discuss too much part of above the melting temperature. So Dulong-Petit law is this one, that is a 3RU. So this straight line which shows the constant specific heat, CV is constant, and that is when you are approaching to this one. But in between the approach and the zero, you are varying with the TQ behavior. Okay, so as the material will changes, their approach will be different. That means a rising of the temperature specific heat with respect to temperature, that is with the different slopes, so that you can understand it. Okay, so classical theory, which is known as the Dulong-Petit law, they have given some assumptions to proceed with the concept, and they said that each and every solids consist of a large number of the atomic atoms, and you are going to treat this atom as a atomic particle, and they do execution of the simple harmonic motion across their equilibrium position. The earlier lectures, I think, for vibrations in a one-dimensional model or vibrations of in a one-dimensional केस फॉर डायटमिक और द मोनोएटमिक, उसमें हमने काफ़ी वीडियोस और ग्राफिक देखे इन माय प्रीवियस लेक्चर्स. तो आपने वहाँ पे देखा था कि एटम्स आर वाइब्रेटिंग अक्रॉस इट्स इक्विलिब्रियम पोजीशन. तो ये इक्विलिब्रियम पोजीशन के आसपास एटम वाइब्रेट कर रहा है. सो नेचुरली यू हैविंग अ टेंडेंसी टू विजुअलाइज दैट एटम इज़ डूइंग सिंपल हार्मोनिक मोशन. और ऐसा एटम जो सिंपल हार्मोनिक एग्जीक्यूट कर रहा है, सो नेचुरली यू कैन टेक एज अ एटमिक हार्मोनिक ऑसिलेटर or in general atomic oscillators. This atomic oscillators will vibrate with the same frequency. That is the second assumptions they have done. पहला assumption ये किया कि एटम equilibrium position के आसपास वाइब्रेट कर रहा है ताकि हम उसको atomic oscillator बोल रहे हैं, and they are showing us simple harmonic motions. Okay, तो एटमिक ऑसिलेटर्स बोल सकते हैं. एटमिक ऑसिलेटर के बाद दूसरा एजम्पशन ये है कि ऑल वाइब्रेशंस, ऑल एटम्स इन द क्रिस्टल्स आर वाइब्रेट विद द सेम फ्रीक्वेंसी. सभी फ्रीक्वेंसी से एक ही फ्रीक्वेंसी से वाइब्रेट कर रहे हैं, राइट. बट स्टिल दे हैविंग अ डिफरेंट एम्पलीट्यूड्स. सो दे मे हैव अ डिफरेंट एम्पलीट्यूड्स, बट दे हैव द सेम frequencies, and their energies are different because of that they are vibrating with the different amplitudes. शायद आपको ऐसा लगे कि अगर सेम फ्रीक्वेंसी से वाइब्रेट कर रहे हैं तो एम्पलीट्यूड कैसे डिफरेंट होगा, राइट. सो देयर एनर्जीज आर डिफरेंट, एंड बिकॉज ऑफ दैट दे आर वाइब्रेटिंग आर with the different frequency. So आप ये भी सोच सकते हो कि when you are going to heat up the any materials, right? So the absorption to a certain region, the heat will be faster, so that energy will be different than the energy associated to the atoms which is little bit far from the source of energy. So they are vibrate with the different amplitudes. ओके सो तीन एजम्पशंस हुए, एक तो एटॉमिक हार्मोनिक ऑसिलेटर्स है, वो सिंपल हार्मोनिक मोशन दे रहे हैं, all are vibrate with the same frequency but they may do have a different amplitudes as they have a different energy. Once they have a different energy, you can think about their internal energy is largely contributed to the vibrational energy. So their internal energy is absorbed and they will increase, and therefore they will do the large contribution to the vibrational energy. The fourth assumption is that there is no restrictions for assumption as you consuming the energy right from 0 to infinity, which is very unusual, because nowadays the specific heat is considered as a terms of phonon, and phonon is exactly the concept of the quantization concept or the quantum concept, but that is come later on after the Dulong-Petit law, almost after 10-20 years later. But anyway, in those days he has also one restriction, that energy doesn't have any boundaries. The atomic harmonic oscillators can consumed energy as much as it possible, as many as it possible, as much as it possible, and it may be run in between 0 to infinity, which is weird, but it is, that was the assumption in those days. And total energy of a crystal at a given temperature is, let us say, n times of energy associated to or average energy of an one atomic harmonic oscillator. मान लो कि आपके सिस्टम में 100 एटम्स हैं, तो आपने एनर्जी ऑफ अ वन एटॉमिक हार्मोनिक ऑसिलेटर ढूंढ लिया, लेट अस से इट इज़ अ x, then the total energy associated to your crystal, that would be n into x, because n आपके total number of atomic harmonic oscillator है, एक एटॉमिक हार्मोनिक ऑसिलेटर्स की एवरेज एनर्जी ई है, तो आप सिंपली उसको मल्टीप्लाई कर लो, राइट. सो विद दिस कंसेप्ट the total energy of an atomic harmonic oscillator, so I do have only two part, one is the potential energy, another is the, in a classical theory, okay, and another is the kinetic energy. So I add up this both, and then I will do the integration according to, because potential energy is 1/2 or the fdx, and fdx is where I can say the force constants, and this is a displacement is x in between 0 to x, and therefore it become the outcome is m omega square x square by 2. So with this logic we do have the total energy associated to the equation as per the 7.5, that is a square of momentum divide by twice of the weight of the atom and the potential energy. With this, if we do some integration and rigorous mathematical work, the average energy, the bar is there, so average atomic energy associated to one atomic harmonic oscillators, the kinetic contribution is kT by 2, and the potential contribution is also kT by 2. So if we add up this, then it will be a kT. So now if you having a think of that this average energy, and they do vibrate across the 3 degree of freedoms. That means they can vibrate along the x-axis, they can having a energy, and they can vibrate along the y-axis, they having a energy, and they can vibrate along the z-axis, क्योंकि 3 डायमेंशनल स्ट्रक्चर में ही हम विजुलाइज कर रहे हैं. So in this case we will be having a total energy associated to the system is 3 kT. Suppose we having a n number of atoms in 1 mole of substance, so my total energy become 3 kT into n. So that is my total energy. Now it is not the average energy, but it's a total energy, right? Nk is nothing but the Rydberg constant, so replaced by R. Okay. Now rate of change of energy with respect to temperature. So rate of change of energy dE by dt will give me the specific heat at a constant volume, with the condition that volume is not changing. So 3 RT will become the 3R, and that is what the Dulong Petit law. This is what the Dulong Petit law. But as I told you in beginning, this is not true for the lighter element, as it is written in the bottom part of the slide, that this law is however fails in the case of a lighter element like a boron, beryllium, carbon, etc. With this, classical theory of a specific heat is finished. The next theory will be Einstein theory, and that would be my last lecture. If this will be the syllabus of the CIA 2. Stay home, stay safe, all the best.